So I'm going to work on an example problem relating to the material in section 1.9 dealing with change in momentum. So here's the problem. You're driving a car with a velocity of 10,0,0 meters per second. A short time later, you are driving with a velocity of 30 meters per second in the direction 0, -1, 0. Your purple VW bug has a mass of around 1,000 kilograms. Find the change in momentum of the bug and give your answer in terms of a unit vector and magnitude. All right. Now, when writing these answers out, it's really important that you have kind of a structured problem-solving format. It turns out this is one of your learning objectives because being able to express your ideas in a very clear fashion is an important part of being a professional, but it also does help you learn the physics because sometimes you won't know how to approach a problem, but if you have this problem-solving format, you can at least start. So first thing I'm going to go ahead and do is just draw a little sketch of the situation. So we've got our little VW bug, and it's got some velocity v initial, and at a later point in time, actually the bug's more rounded, it has some v final, and we have a bunch of known information, and we should write down the variables for all of that information just to see what we have. So the mass of the bug is 1,000 kilograms. The initial is 10,0,0 meters per second. V final, and I'm just going to go ahead and combine these as 30 meters per second times 0, -1, 0. All right, and what we're trying to find ultimately is delta P. All right, so going to a new slide. Let me write down the equation that we're going to be working with. There's really two equations that we need. We need the definition of momentum, which is P is gamma mv, and we also need delta P equals P final minus P initial. Now, we notice that since the velocities are much less than c, that implies, as we saw in previous section, that gamma is approximately 1, so P is approximately mv. When gamma is roughly 1, then this is just going to reduce down to mv. So it's important that you recognize this fact. When you're writing out these momentum problems, you want to start with the relativistic equation because this is the correct equation. This is only an approximation, and you need to show that this approximation is valid in this case. All right, so I'm ready to go ahead and start solving. So we have that P initial is M V initial, and again, this is just an approximation, which is going to be 1,000 kilograms times 10,000 meters per second, or 10,000. I'm just going to write this as 10 to the 4 kilogram meters per second, just to be a little concise. And actually, what I should do is to write that as a vector. So that's going to be 10 to the 4, 0, 0 kilogram meters per second. My P final then is M times V final, which is 1,000 kilograms times 30 meters per second times my unit vector minus 0, -1, 0. So that comes out to be 3 times 10 to the 4, and this -1, it's going to give me a negative And I'm just going to leave this as 0. And actually, you know what? Let's leave the -1 in there. -1, 0 kilogram meters per second. So delta P, the change in momentum then, is simply going to be P final minus P initial. So the way to do this is component by component. So let me actually write out the two vectors. So P final is 0, comma, -3 times 10 to the 4, comma, 0 kilogram meters per second minus, and that's actually 1 times 10 to the 4, comma, 0 kilogram meters per second. And so we just do this component by component. So the x components, 0 minus 1 times 10 to the -4 is -1 times 10, to the +4. And -3 times 10 to the 4 minus 0 is -3 times 10 to the 4. And 0 minus 0 is 0 kilogram meters per second. All right, so there's my delta P vector. Now the next thing is I need to find the magnitude and the unit vector. So the Pythagorean theorem is what we'll use to actually find the magnitude. So the magnitude of delta P is essentially the square root of delta P x squared, that's the x component of delta P, plus delta P y squared, that's the y component of delta P, plus delta P z squared. And that will give me the magnitude. So the x component was, let's go back for a second, -1 times 10 to the 4. So -1 times 10 to the 4 kilogram meters per second squared. The y component was -3 times 10 to the 4 kilogram meters per second. And the z component was just 0 squared. And we take the square root of all of that, and we end up with a magnitude of delta P equals 3.16. Let's just run that up to 3.2 times 10 to the 4 kilogram meters per second. One thing I do want you to notice is that our components, we had 3 times 10 to the 4 and 1 times 10 to the 4. Our magnitude is a little bit larger than the largest individual component. Because this term, even though it's 1/3 the size of this component here, when we combine them in quadrature, we combine them using the Pythagorean theorem, this term right here is the dominant term. And so we end up with something a little bit bigger. So to find the unit vector, delta P hat, and that's just the normal vector, delta P, over the magnitude that we just calculated, delta P magnitude. So the vector is -1 times 10 to the 4. And let me move the units outside the vector. -1 times 10 to the 4, -3 times 10 to the 4, 0 kilogram meters per second, all over 3.2 times 10 to the 4 kilogram meters per second. Now, one thing I want you to notice, with the unit vector, the units have gone away. Unit vector, despite their name, have no units. That term unit vector is referring to the fact that it has a unit length, a length of 1. So my unit vector, delta P hat, then is simply, let's see, -1 over 3.2, comma, -3 over 3.2, comma, 0. There you have it. Here's my unit vector. It has no units. My magnitude has the same units as momentum. So everything looks pretty good. For much of the book, we'll be dealing with vector quantities quite a bit, so it's really a good idea that you get really comfortable working with them. One of the symbols that will come up quite frequently is delta. And delta, whenever you see that, it means essentially change in whatever comes after the delta symbol. So this equation right here, delta P, is simply the change in P, the change in momentum. And whenever we're looking at a delta, it's always going to be final value minus initial value. That's always true with the change in some quantity. It's going to be the value at a later time minus the value at an earlier time. So let's say that we're dealing with P initial, P final, and we'd like to know what's the change in momentum in going from this point to this point. So what we're going to do is graphically subtract these two vectors. And that involves placing the two vectors tail to tail. So P initial here, and then P final like that. And we start at the nose of whichever vector we're subtracting, in this case the P initial, and go to the nose of the other vector. So this right here is my delta P, my change in momentum. Another way to look at this is saying, if this is my initial momentum, how would I have to change things to end up with my momentum going in this direction? Well, I'd have to add to P initial a vector along this line to end up with momentum in the direction of P final. And you can see that from this equation pretty easily. If we go ahead and rearrange this by adding P initial to both sides, an equivalent equation would be that P final is equal to P initial plus delta P. This is really kind of an important concept to understand right here, that if we know what some value is initially, it goes through some change. If we add those two together, that gives us our final value. So let's take a look at another example, and let's ask, well, what's the change in momentum between these points here? So what we do is we break this up into little time chunks. So let me look at just this part right here, in which case my P initial would be PB, my P final would be PC, and so I'm going to call this delta P B C. That's the change in momentum between points B and C. So that's going to be P final, which in this case is PC, minus my P initial, which is PB. And if I'm going to graphically subtract these two, again, we put them tail to tail. Here's my PB, here's my PC, and start at the nose of the vector that we're subtracting and go to the nose of the other guy. Right there, that's my delta BC. So again, another way to look at this, if my momentum is initially in the direction of PB, which way do I have to change it to end up momentum PC? Well, my change would simply be like this. Here's another way of thinking of it. If my PB is pointing this direction, which way would I have to go ahead and pull on that vector to get it in the direction of PC? That's really what the change is. It's pulling on that vector to get it moving in a different direction. So then we would look at the next time interval, and this next time interval, which my change in momentum then we'll call delta P CD. Now, this is my momentum at a later time. This is my P final for this time interval. So it's PD minus my momentum at the start of that time interval, which is PC. So if we go ahead and draw these guys, let's see, PC looks like that. PD looks like that. Subtracting these two, start at the nose of the subtracted vector and go to the nose of the other guy. And there's my delta PCD. Again, my momentum is originally in the direction of PC. how would I have to pull on that vector with my hand to get it going in the direction of PD? So take a look at this section and make sure that you're pretty comfortable with calculating this. It's more important that you calculate it numerically, but understanding how to do this graphically is an important skill because it will help you kind of gain a gut level understanding of what exactly is going on and what some of these things mean.